And but now let's formalize it through Callan's postulate number 1. And also, please get hold of Callan's book. It's an old book, but it's nice. Me and another professor here, we always think about if there is a book that could replace it. Somehow there is not one yet. Scott Shell's book comes a bit close, but still not quite there. So you can buy the book or do whatever you want, but please go through it. So Callan's first postulate tries to make it explicit that equilibrium states exist. So write down this statement, and then this postulate is not going to be that complicated. You will get a feel for why such thing might be true. The second postulate, which we'll do, is a bit more complicated. We will do that one also today. So Callan's postulate says there exist equilibrium states that are macroscopically characterized completely by internal energy E, volume V, and number of particles N1, N2, N3, depending on if you have different types of particles. It's a multi-component system, right? Otherwise, you can just collectively call this as N. If it's a one particle system, if it's only oxygen, for example, it's just N. This, it continues for a little bit more. This macroscopic equilibrium state will be independent of which non-equilibrium state we started from. In other words, it will be what is known as path independent. So this is Callan's postulate number 1. Let's try to understand it. So the most important sign of equilibrium is it should not matter how you created the system. You are doing an experiment in lab, and you do a particular procedure to get to the final equilibrium state. And you measure some macroscopic property of this system, heat capacity, thermal expansion coefficient, whatever, and you get some values, okay? Now, how you created the system, how you got there should not make a difference. So this can become more concrete if you look at the example of what we did of the internal constraint example, right? So we said that we had an internal constraint that was right here in the middle, and we had NA, NB on the left hand, NA and NB, VA and VB, so on and so forth, right? And then we removed the constraint, or we allowed it to move and everything, and then we got to an equilibrium state, right? Now, we could do something else. We could have put this constraint, the same system, but we started the constraint from somewhere here on the right, okay? So it's a different starting point. And now we allow the constraint to move to the left and right. Once you establish pressure, do you expect it will make a difference? It won't, right? If you truly allow mass to exchange, energy to exchange, and what was the third one? The volume to change. It does not matter where you started, right? If this sounds abstract, think about it this way. All of you have been on a swing at some point, right? So if you're on a swing, whether I start you from up here, or whether I start you from here, or whether I start you from here, doesn't matter. In the end, you will oscillate around the middle, or you will just come to rest in the middle, right? So true equilibrium state does not make any difference where you start from. If it is making a difference as to where you started from, then you're not reaching equilibrium. So for those of us who do, like my lab does computer simulations, this means that if you prepare your system a certain way, you should prepare it 3 different ways. And if the final answer is different, depending on how you prepared it, then you have not reached equilibrium in any of them. You might have reached equilibrium in one of them, but you cannot be certain. Now, if starting from 3 different positions, you're getting to the same macroscopic state, then maybe you have reached equilibrium. It still cannot be certain. But if it's different, then it's definitely not equilibrium. So this is Callan's postulate number one. Once you start reading the book, you will see that Callan has actually three postulates. We are not going to do the third one. We are just going to do first and second. And invariably, one of you will come and ask me, if you read the book, that why are you not doing the third one? And we will use the third one at some point. But for now, we are not going to use it. Any questions about this? So this is talking about macroscopic properties, right? Again, going back to the swing example, where you come in the middle, if some microscopic properties might be different, but overall, it's going to be the same. So let's define these. So what did I mean by this figure? What I meant with this figure is that they will reach the same equilibrium state. It does not matter how you started. So let's try to understand a little bit what we mean by macroscopic properties. So we already saw three. We saw number, we saw volume, we saw internal energy, right? How do you calculate the internal energy of a system? Where does it come from? I have to familiarize with everyone's names. I'll just ask. Lynn, what do you think? What contributes to internal energy? Kinetic energy and potential energy, right? That's it. There is nothing else. Okay, it's a trick question. So internal energy is the sum of kinetic energy plus potential energy, right? And you're a physics undergrad, right? Yes. So if the Hamiltonian is separable, these can be calculated separately, right? They don't talk to each other. But that's another discussion. So internal energy E is a sum of kinetic energy plus potential energy. Similarly, you have volume V. That's obvious what a volume is, and number of particles you know. So these three are macroscopic properties. On top of that, they are a special type of macroscopic property. They are extensive macroscopic property. What do I mean by extensive? They double if you double the number. Clearly, n doubles if you double n. That's trivial, right? But volume also doubles. Is that always true? That volume doubles if you always double the number of particles? You can imagine scenarios it's not true, right? But that means that you're not in equilibrium. Okay? Extensive means linear in n. So energy is linear in n, potential for a system in equilibrium. Volume is linear in n, and number trivial is linear in n. But these are not the only macroscopic properties. You also have intensive macroscopic properties, which stay the same if you double the number of particles. Let's go to Suvadhi. You're Suvadhi, right? Okay, good. Don't worry, I will stop asking questions later, but right now I want to familiarize with people's names. So can you think of a property which is macroscopic, but does not change if you increase the number of particles? Let's be careful. Temperature is not a property of the system. Temperature is a property of how you interact with your environment. Okay? So nope, not temperature. What if I divide number by volume? Does that have a name? Density. Density is a macroscopic property. We call it rho, right? And density, it's a ratio of two things which depend on n linearly, right? So density is intensive. Can you think of other intensive properties that are not just a simple ratio of two things, but slightly more complicated? Anyone? How about thermal expansion coefficient? Thermal expansion coefficient is defined as change in volume. I'm talking about volume thermal expansion. Change in volume, partial V, by partial T at constant pressure, 1 over V. This is a macroscopic property. Now, why is it an equilibrium property that's subtle? And we will be looking at it later, right? Because I just told Subhadip that no, don't talk about temperature because that depends on the environment. But I have put the temperature in the denominator here, right? So The claim I'm making here is that if you prepare a system, if you bring it to equilibrium, then the thermal expansion coefficient is going to be path independent. It won't matter how you prepare the system. This should shock you. Well, first you should think that is trivial because that's all you have thought about in your life till now. But now you should be like, why should it be independent of this? It's not obvious from what we have done so far, right? So because Callan's postulate says that equilibrium states are characterized completely by internal energy, E, volume V, and number N. Why these three? Because energy corresponds to thermal equilibrium, volume corresponds to mechanical equilibrium, and number corresponds to chemical equilibrium. So we are talking about three types of equilibrium, and that's why there are three things for a complete system, if there is nothing missing. So this is true for, so that's our starting point. Any question? Okay. Can you think of other intensive properties that could be macroscopic and depend only on equilibrium? When you characterize a material, be it a battery, be it a polymer, be it whatever, you report some properties on it, right? Most of you here have done way more experiments than I have. What properties do you measure when you characterize a material? Go ahead. Molar mass, but a good point. That's kind of in the intensity category. Keep thinking, what else? Color is a good one, but then that's a good one. You have to throw some light on it, right? There won't be any color if there is no light. Right? Heat capacity, that's the one I was looking for. So, Anjali, how do I define heat capacity? Change in heat, but that gets even funkier. And we are going to get comfortable with these symbols as the semester proceeds. It's a delta. It's a squiggly delta divided by a squiggly temperature, this temperature. And if it's constant volume, this is at constant V, divided by 1 by N. So you can see Q is extensive. The amount of heat you need to give something to change its temperature will double if you increase the amount of quantity. So you divide by N. Why is heat capacity, however, dependent only on equilibrium? Why is heat capacity? Why are these two path independent? That's not clear as of now. We will get there in a little bit, okay? But these are examples of properties. Again, this is intensive because the numerator is extensive, the denominator is extensive, and you divide by both, so you get an intensive property. And when you said the color, I think you could define property, but I would think about something more like refractive index or something, right? Yes, but you're correct. Color is really a spectrum, right? So, good. So, the last time we tried to define thermodynamics, now we can try to define it a bit more rigorously as to what it is all about, and I will write it down. So, thermodynamics . I should just go out and be like, when I become 60 years old, that's what I will do. Thermodynamics is the study of time independent. There's no notion of time properties of equilibrium states, which can be described with very few variables, equilibrium states of macroscopic systems. So I want to color a few important things here. So first of all, time independent. There is no notion of time. We are not talking about how anything is changing as a function of time. It's only once equilibrium has established what it's going to be. Equilibrium states, right? So you have to get to equilibrium, which the first postulate tells you that such states exist of macroscopic systems. This I want to talk about a little bit more. What do I mean really by macroscopic systems? So there is a term that keeps getting used every once in a while, especially when you go to StatMech in next semester, which is known as thermodynamic limit. Thermodynamic limit is defined as n tends to infinity. You have lots and lots of particles. So Avogadro number is a huge number, right? 10 to the power 23. V tends to infinity, volume tends to infinity. The volume is actually really, really large, while their ratio is finite. The density is finite, and these two go to infinity. This is the thermodynamic limit. So when you go to StatMech, every once in a while, you will see some contradictions. Has anyone here heard about negative temperature? What do you know about it?
It's basically if you can like cap the amount of maximum energy you have in the system, as you add energy, entropy decreases.
Absolutely. But did you know that negative temperature is hotter than absolute zero? It's amazing, isn't it? So you will read about negative temperature in 687, and the reason it happens is because he said you cap the energy. In thermodynamic limit, you cannot cap the energy. Things are big; they are really, really big. You cannot say this is the maximum energy you can have. You can always add more energy, right? So it's lots and lots of degrees of freedom. You can always keep adding more things. So this is thermodynamic limit. And in this semester, we will stay in this limit. We will work with large enough that we can keep adding more if needed, but it's not a small number. Any questions? So that's a term that will come up. No questions? Okay, that will come up again and again, thermodynamic limit. Another term that I have been using already, and I want to be rigorous about it, is system, surroundings, and universe. What do you know about undergrad? What's your name? Remind me again.
Undergrad.
No, come on, man. Tell me. You're not in my photos.
Yeah, I'm on class. I'm
John, right?
Jock.
Jock.
Sure.
That's a cool name. No, it's not J-O-C-K.
It's J-A-C-Q-U-E-S.
Oh, very fancy. It's like a French name.
Yeah.
Are you from France?
My dad was here.
Oh, very nice. So, Jock, so why do you know about negative temperature?
I saw a lecture by Bill Phillips where he brought it up, and I thought that was really cool. And then
Bill Phillips, the Nobel laureate. UND is only Nobel laureate at the moment. So we want to talk about these three things: system, surroundings, and universe. And what are they? So system is part of the world we choose to study. Okay. Surroundings is part of the world we know it exists, but we don't study really, or it's I won't call it we don't study. We know it exists, but we keep it separated from system through walls. So there are some walls, and we will talk about walls in just a bit. And universe is simple. It is simply system plus surroundings. So nothing exists outside it. Okay, we don't even know if it exists. We assume there is nothing. So for example, you could have a cylinder in which you have this system, and maybe it's a system made up of some gas molecules, and you are using a piston to apply some pressure on this gas molecules. You are compressing it like that. So we will use these piston type examples a lot, even though we really don't use. Is there anyone who uses piston in their real life to do something? Like in their lab life? Kathy, do you use piston? Megan uses like piston cylinder or something, no? Yeah. You, good for you. It's very scary. But, does anyone here who uses a fountain pen? But you know what it is, right? A fountain pen has like a syringe or a piston. But when thermodynamics started 200, 300 years ago, people were interested in steam engines and things like that, right? So they would compress a lot of things and make energy out of it, right? So most of the examples are from this piston type examples. So we have piston, which is compressing a system. And then the whole thing is maybe exchanging energy or maybe not through surroundings, to its surroundings. So we know it's in the absence or presence of, there is something outside the system. And together we cap both of this and we say, this is our universe. And we draw such hatched lines outside, showing that nothing can definitely exchange. Whenever I draw the hatched line, it means it's blocked. Nothing can go in and out, okay? You might or might not have exchange between system and surroundings, but definitely no exchange outside surroundings, outside your universe. So, and these things are our walls, okay? We are interested, there can be many types of walls. There are two types of walls we will be talking about quite a lot. One is called an adiabatic wall. No flow of thermal energy. So an adiabatic wall is such, can you think of an example of an adiabatic wall? It's a, what? Insulated flask, right? Where is my coffee? This is not an adiabatic wall, right? Even if I cover this, it's not adiabatic, but a proper flask or a furnace in which you're doing some experiment should be adiabatic. So no flow of thermal energy, while a wall through which energy can flow is not called non-adiabatic somehow. Sorry, it's called a diathermal wall. Energy can flow, okay? This adiabatic concept is quite important. So together, the system plus surrounding, the universe, the wall that is outside the universe, it's an adiabatic wall, right? Nothing can go in and out. It's completely trapped. So that's an example of an adiabatic wall. Any questions about this? Okay. So let's recap just a bit before we go to the second postulate. So what have I said so far? Callan's postulate number 1 says that there exist equilibrium states. So it's really telling you that there is equilibrium, because how do you know that there should be equilibrium states? How do you really know? And in fact, this is a good point for me to mention the thought experiment. No, it was thought experiment for me, but active experiment for all of you when you try to move around, right? So I followed you as a time average, right? I followed your trajectory as a function of time. And I said that if I follow it long enough, on the average, you will be somewhere in the middle. So this operation is called a time average. This is not the only way to average a system. I could do something else. I could make, it's kind of like a parallel universe. I could imagine 100 other copies of this system. In one of them, Anjali is sitting over there, and Jock is sitting over there, and things like that, right? In another one, Subhadeep is sitting over there. And I could make a million, a billion, a gazillion copies of these systems. And if I averaged over these different copies of the system, that is a different type of average. That is known as an ensemble average. We are not going to do that over here. In 687, next semester, you will start from that. And there is a principle known as the ergodic hypothesis, which says that these two averages are same. But again, if you're interested, you can talk to me more about it. But for now, let's come back. We are talking about that there exist equilibrium states which are nicely characterized. And if it's really talking about an isolated system, okay? If a system is isolated, you cannot exchange mass out of it. You cannot exchange particles out of it. You cannot have volume fluctuations in it because it's isolated. And you cannot have energy transfer inside or outside of it, right? So it should be fully characterized by number, energy, and volume. Such states exist. This is our postulate number 1. This is very abstract, right? It doesn't really give you much to do with. Callan's postulate 2 is what really starts introducing the machinery. And suddenly we are going to enter a bit of math. And we will write down Callan's postulate number 2. And then over the next couple of lectures, I will try to give you intuition into why such a postulate might be true. The first postulate, you can see why it exists. We know equilibrium exists from personal experience. The second one is complicated. Callan's postulate 2 says, so the first postulate just told us that equilibrium state exists. Callan's postulate, second postulate, gives us tools to characterize this equilibrium state. What will it look like? What is this equilibrium state? This says that there exists an extensive and I'm going to color this in red because this is so important, state function. By state function, I mean, it does not mean how you prepare the system. It is path independent, okay? Whichever way you go, this function will stay the same. And thermodynamics is really all about figuring out state functions versus path functions. There exists an extensive state function, which we are going to call S, that depends on NVE. So we can write it as S as a function of NVE, which is, so Callan's postulate 2 is made up of many, many parts. This is the first part, okay? That there exists an extensive, again, it's loaded. It will double if you increase the number of particles. There exists an extensive state function, S of NVE. So that's our first part of the postulate. And there are going to be like 3 or 4 more parts, which is defined for all equilibrium states. This is our second part. For any equilibrium state, you can define such a state function. Furthermore, if you differentiate this state function with respect to energy at constant number and volume, it is positive. If you differentiate this state function with respect to volume at constant number and energy, it is again positive. If you differentiate this state function with respect to number at constant volume and energy, it is again positive. So that's 3, 4. We have 5 parts already in this postulate, okay? So it's a state function that depends on 3 variables, and it is monotonic increasing in any of those variables if you keep the other 2 constant. What does this mean? Let's draw a graph, okay? And let's try to get intuition, for example, for this one. So let's say I'm drawing a graph of S versus E at constant N and V. Is this a possible state function? Is this a possible function for S that changes with energy like this? Why not? It's negative, right? So this one is not permitted by Callan's postulate. How about this one? It's permitted, right? How about this one? Who thinks this is permitted? Raise your hand. Who thinks this is not permitted? Why do you think it's not permitted? No, but the slope is always positive. Later we will see in the red and the blue, actually only one is permitted, the concave one, and that will come later. But as per this point, what we have written so far, both are permitted. The slope is always positive. The slope is becoming smaller and smaller and smaller. But I'm not saying that at some point it will start doing this. No, I'm just saying it's like a log of x. Okay, just goes up and yeah, go ahead.
The slope might become 0 at some point, right?
Slowly.
But the postulate says it's greater than 0, not
there will exist an epsilon between the slope and 0. And that's good enough for us if you want to bring in real analysis. Okay, it will be some very small. Okay. Later we will see that only one of these 2 is permitted. And that's going to happen in a bit. So why does this exist? I will try to give you intuition. It's not easy. This is where Callan's book is like, yeah, whatever, just take it. If you don't like it, you bought the book, you're stuck with it. But I will show you why this makes sense. And later we will also see that this is actually 1 over temperature. This is the most accurate definition of temperature. So next time someone tells you, how is the weather in College Park? You can be like, oh, I haven't quite measured the partial of S with partial of E at constant N and V in a long time. Nerd joke. So we will see that in a moment as to why that is the temperature. So this S exists, which depends on NVE, and all its 3 partial derivatives are positive. Okay, these are postulates. I'm not trying to prove this at point. I'm just trying to throw these on you. And I will give you intuition as to why they exist. I cannot prove this though, I can only give you intuition. The final one, which is a bit, it's a bit long, but it's important. So I wrote down 5 things that I colored in red star, and I'm going to write down the final one, which is that if a state A of a system is adiabatically accessible from some other state B of the same system, then SA must be more than equal to SB. In other words, the delta S for an adiabatic process is more than equal to 0. Now that's complex, but that is something you all have seen previously. This has a name. Anyone knows what's the name of this one? Right?
Entropy.
Well, S is entropy. We are skirting around, yeah, but this S is called entropy. But this statement that I wrote, the 5th one, what you're Stephen? Stephen?
Yeah.
What's its name? Do you know the name of this statement?
It's one of the laws.
It's the second law of thermodynamics. So let's go back to our cat staring at the ice cube example, and clearly most of you are cat people. Was there a single dog posted on the cat channel? I don't think so. There's a horse, there were cats, but no dog. Disappointing. So an ice cube melts, right? If you keep it at room temperature, you put it over here, it's just going to melt. It's not going to suddenly come back and refreeze. Or even better example, if I take this coffee and pour it on the ground, it will just spread. The opposite process that the coffee just picks up from the ground and collects in my cup, that's not going to happen. Unless you design a very, very fancy machine that picks up every single molecule and brings it back into the cup, right? You can do it. You can do it for sure. But it won't happen in an isolated system, right? Or no way it can happen in an isolated system. In an isolated system, there's a clear direction that is preferred. And in an adiabatic system, to be more precise, right? If you pour, the coffee is more likely to just fall down on the ground. Or let me give you another example. If I break an egg, it's just going to get on the ground and break in different parts. It's not going to reassemble. Third example, if I drop a ball on the ground, it will bounce, 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 and then kind of stop, right? What's going on? It is losing energy to the ground, right? And every time it bounces, it loses some more energy. The opposite process, where the ball is just sitting over there and suddenly starts to suck up energy from the ground and comes back up again. It's not going to happen, right? Unless I'm doing something complicated. So you can see there is a preferred direction. And so that's what this Cullen's postulate says. You cannot prove it. Second law of thermodynamics cannot be proved. There is no known violation. In fact, my colleague here, Chris Jarzynski, he gets emails, I think a couple of emails every week from someone in India, Brazil, China, US. I think I have found a violation of the second law of thermodynamics. And then he's so like some people are excited about football or cricket or running or whatever. He's like really passionate about second law of thermodynamics. He stops whatever he's doing and he tries to find a contradiction in the violation. So I think he could write a book one day. 100 times you thought second law of thermodynamics was violated, but it wasn't. And most of the times it's because it's not an isolated system, right? You're not looking at system plus surrounding, you have something else going on, and that's doing something, right? So, and so this S that I just wrote down is called entropy. And again, there is no known violation of this postulate, but you cannot prove it. And The only reason why it might exist is that the universe itself started in a very low entropy state and is kind of evolving towards, I'm using the word evolving loosely here, towards a very high entropy state, right? And you can kind of see why it might make sense, right? The Big Bang, everything was really packed in one time spot. And it's just like expanding and becoming more and more chaotic, kind of this. So this entropy is very different from the entropy often you all get taught in PChem, which is S is equal to K log W. And that's easy, right? It's easy to teach. Often people who don't do theory also like to teach it because it's so easy and it gives you something to calculate, right? K log W, just calculate number of A's and there you go, you get your entropy. This, I haven't told you anything. Can you calculate this F of NVE? Nope, I've just told you it exists. I've not given you a recipe to actually go and calculate it. And in thermodynamics, I will never give you a formula to calculate S. I will only tell you it exists. However, I will give you a formula to calculate delta S. And that's what really matters, right? Delta S tells you whether a certain process can happen or not. That's all we really care for. You made a protein. Is the protein going to stay folded or is it going to become unfolded? Calculate the delta S if it's a truly isolated system. Most of the times it's not isolated. You have a protein in a beaker in contact with something else. We will introduce equivalent state functions, which are known as free energies. But you will have similar relations for those free energies. So what really matters is calculating delta S. And that's what we are going to do in the rest of this semester. Any questions about this? Yeah, if you think of a second law of thermodynamics violation, please email Chris and copy me. It's a lot of fun. Last time when I taught this, there was a Russian guy, Alex. He's a lot of fun. Do you know anyone knows Alex Freeman? You should go find him. He's in biophysics. He was like, oh, I have found a violation. So and he emailed to Chris, and Chris wrote down like a 2-page long email trying to find this. And effectively, the point was that it was ignoring that the sun is putting some energy into the process, right? So anytime there is a violation of, like many people say, I mean, I will go on a tangent here, but like evolution violates second law of thermodynamics, things like that, but not really because we are sucking in energy from an external system, right? So things like that. So what have I done so far? I have told you there exists equilibrium states that can be characterized fully by NVE. That was the first postulate. And the second postulate, that for such equilibrium states, there exists an extensive state function, which depends on NVE, because that's all you need to characterize them, right? And it has these nice mathematical properties, which I will give you some intuition in the coming classes. And what is even more important, or as important, is that if a state A can be accessed adiabatically from a state B, the state function, entropy, must increase. It cannot go down, okay? It can stay the same. Which brings me to the next point is, if SA is more than equal to SB, and SB is more than equal to SA, what does it tell us about the preferred direction? Is it going from A to B or B to A? It doesn't tell us anything. Then it is A to B, B to A, both are possible. And we have a reversible process. So an egg falling down on the ground is not a reversible process. Clearly, only one direction is preferred, right? Similarly, coffee falling on the ground or coffee cooling down is a irreversible process, right? It can go only in one direction. Can anyone here think of a truly reversible process that can happen in both directions in an isolated system? Yeah, when you have chemical equilibrium, you can have reversible processes. And that's really why chemical equilibrium exists, right? When you attain back and forth in both, and we will study that towards the later part. So another way of thinking about this is that a reversible process is one in which S stays constant, right? It's not changing, while an irreversible process is one in which S increases. So what I said, let me, yeah, go ahead. Uh-huh. So you prepared it in some equilibrium system, some equilibrium state, and it can go to some other equilibrium state. Sure. So the final state that you attain is an equilibrium state. You prepared it in some non-equilibrium state. Sure, sure. Good point. So, very good point. So, what Venkat said is, I have not made any claim about entropy being defined for non-equilibrium state, and in fact, it isn't. So, if I prepared, so this is where we have to be careful about. So, what I'm stating here is that, let me try to think of a certain example. So, what is your contradiction here? Tell me again.
Other than the case where it's equal, assume that SA is greater than S. When you start at state B, you go into state A.
Yeah.
Isolated.
Yeah.
So that means A is the linear system state B, it's not state in B, so that's not equilibrium. B is not an equilibrium.
Yes, let me try to answer it carefully. So, okay. So you are saying that if it's, no, so okay, we have to be very rigorous here. At no point did I say that equilibrium state is one where you get there and you never leave it. You are confusing with that.
Either B and A are same, or NDE define both B and A, then they can't be same.
Okay, so let's draw a graph. N, V, E, okay? Should I draw in 3D? No, I should not try to draw in 3D. Let's ignore N for a little bit, okay? Let's just worry about E and V. So here I am going to have a function S of EV, right? That is uniquely defined for any particular value of E and V. Okay, so I have drawn a contour line over here. So all of these are the same value of entropy. Now, and let's say this value is 10, some number, okay? Now I draw another contour line. Over here, the value of S of EV along all of these states is 8. What I'm saying is you can go from this one to this one, but you cannot come back. So there is no contradiction in this. That's it. That's all I'm saying. Let's discuss this point. There is no need to rush.
I do have a question.
Yeah.
I mean, I understand that it's a matter of microspace, so it's a matter of probability.
No probability, no microstates in this semester.
But I mean, so it cannot go back to the same state because probability of being able to read the same microstates is dependent.
So when you build up these notions of probability, it seems familiar and maybe you can use it to develop intuition, but I would say stay away from it because it can also create confusion. So that's why I'm trying to avoid all microstates and probability and things like that. So if you have taken StatMech before, try to forget it in this semester, okay? It's harder to develop intuition for things this way, but once you take StatMech after this, you will see why it was worth it to do that. So Venkat's confusion is not clear yet. Let's work on it. Are you sure? Are you sure? How is your confusion clear?
So what I thought was basically that there can be no state at like different E and B and we call it EB. But as long as we are saying that EB and N define the state, we
Yeah.
point that out.
Yeah.
That point is defined by EB and N for that.
Yeah.
That is the state.
Yeah, exactly. Exactly. So let's try to write down some possible functions for S of NEV and just to familiarize ourselves with it and see if they are valid or not as per the second postulate. Okay, so I want you to answer. So I'm going to write down S is equal to AE plus BN plus CV, where A, B, C are some constants. Okay, let me write down first, just write them down, a few of them. S is equal to square root of AN square plus BV square plus CE square. S is equal to 5E minus 3N plus 2V. S is equal to AN by BE plus CV to the power 5. And let's call this number 1, number 2, number 3, number 4. Who thinks number 1 follows? We cannot say anything about, so our postulate had 5 parts, right? There exists a function, so that we already wrote down. We cannot say anything about the last one, which is the abstract one, the delta S adiabatic. And we will keep coming back to this delta S adiabatic more. Once we will be drawing some surfaces, and then you will see it becomes clear. I want you to focus on the middle 3. So the first one, does it follow? And let's say A more than 0, B more than 0, C more than 0. Does it follow all the postulates? Right? The partial derivatives with respect to E, N, and V are just A, B, and C. They are all 3 are positive numbers. All good. Is it extensive? Right? It's a linear. How about the second one? How about the partial derivatives? Huh? Good. Is it extensive? You are nodding your head no. Why not? But it's a square root. If I double N, let's assume these are not there, and I doubled N. So what will it become? It will become A square root of 4n square. And what is square root of 4? 2. So it will double. So it actually is extensive. Okay, that's a trick one. How about the third one? Is it extensive? Sorry, it's extensive? Is it? Well, already you can see it does not follow the monotonicity relation, right? The partial derivative is negative, right? That's a problem. If you differentiate this one, if you do partial S by partial N at constant E and V, it is negative. That's not good. That is bad. How about the bottom one? That's not extensive, not intensive. It's somewhere, it's some garbage, right? So that's also not okay. So just to give you some intuition into what it is. But when you do have such a relation, S is equal to S of E and V or NVE, whatever you want to call it, it holds immense importance. It holds so much importance that we call it a fundamental equation. I mean, thermodynamics is a fundamental science enough already, and inside that we are saying this is a fundamental equation, like fundamental inside fundamental. It's like really, really important. What do I mean by a fundamental equation? A fundamental equation is such an equation that if you know it, if you know such an equation, then you can calculate all thermodynamic properties. So it's super important. Later on, we will see, and this is where thermo starts to become fun, at least for me, and hopefully for you all too. is that S is equal to S of E and P, energy, number, and pressure, is not a fundamental equation. So this sounds abstract, but it's quite practical. So let's say you're doing an experiment on something, whatever, quantum gas, whatever it is. And you measure the entropy as a function of energy, number, and volume, and you are able to fit it and get a curve. That's it. You know all thermodynamic properties about it. You want to calculate heat capacity? Yes, we will show you a way to do it. You want to calculate refractive index? Sure, you can do whatever you want. All sorts of thermal, okay, maybe not refractive index, but all sorts of thermal related things you can do. Okay, heat, thermal expansion coefficient you can calculate. At the same time, if I gave you S is equal to S of E, N, and pressure, that is not a fundamental relation. You will see that it misses some information, and we will work through these things through example. Why is this a fundamental relation? Because Callan's postulate tells us that macroscopic states are completely characterized through the knowledge of E, N, and V. Callan's postulate does not tell us macroscopic states are characterized by their knowledge of E, N, and P. It's E, N, and V. That's why this is a fundamental relation. Later on, we will see that, well, quite soon actually, that E as a function of S, N, and V is also a fundamental relation, and we will derive a bunch of them. Does anyone already see why that might be a fundamental relation? Why? Yeah, good. We'll get to that in a moment, but that is the key idea. So we will see why E as a function of S and V is also a fundamental relation, and it really follows from what Venkat said, this monotonicity property. If you keep N and V constant, S and E uniquely determine each other. And we'll see. So when I asked you about your favorite math equations last time, someone said ideal gas law. Who was that? What's your name? Okay, Mari. You're in my, are you registered already?
Yes.
Oh yeah, Mari, Caroline, Suzuki. Okay, Mari. So you like ideal gas law. So do I. What is the ideal gas law? Can you tell me? Is this a fundamental equation? No. It's a no. It's okay if you don't. It's an equation of state, right? So I want to make this distinguishing feature. This is an equation of state, while S is equal to S of NVE is a fundamental equation. Mari, do you know of any other equation of state? It starts with a V and an A and an N, Van der Waals equation. Yeah. So Van der Waals equation states that ideal gas law assumes things are point-like, right? Very, very tiny. Van der Waals says that no, they are not just point-like, and there is some attractive force between them. Right? This is the Van der Waals equation of state. So this is also, so this is ideal gas equation of state. This is Van der Waals equation of state. Does anyone know of any other equations of state? Also starts with a V. V and then an I. I'm playing like that game. What is that game where they have letters? Oh, Jeopardy or something? Huh? Yeah, Wheel of Fortune type game. Yeah, there you go. So it starts with a V, then an I, then an R. Come on. Virial equation of state. Okay, which generalizes Van der Waals. So these are equations of state. What do equations of state do? Equations of state generally tell you how pressure, volume, and temperature for a certain material or chemical change with respect to each other. But that's not a fundamental equation of state. That's not a fundamental equation, sorry. So if you know the fundamental equation, you can go to the equation of state. You can derive the corresponding equation of state. And depending on what is the fundamental equation, you will get a different equation of state, right? And that will change. Ideal gas law is very, very approximate, of course, right? Nothing. But you cannot go in this direction. Just knowing the equation of state won't allow you to get the fundamental equation. Okay, equation of state is missing information. For example, van der Waals equation of state. If you knew the van der Waals equation of state, and I asked you, Maria Delia likes probability. If you knew the ideal gas equation of state, and I asked you, what is the entropy of an ideal gas? Can you calculate that? Can you really do that? If you do it carefully, you might find that there is something missing. There is an undetermined coefficient. We will do this in a homework problem later, okay? So we will see that just knowing the equation of state and trying to get all thermodynamic information, maybe you get the entropy, but there will be some other things that you won't be able to get completely, okay? So you will see that sooner or later, you will see something is missing. You can't do the full thing. But if you knew the fundamental equation, you can derive everything, right? So it's super important. So again, fundamental equation can give you equation of state, but the reverse direction is not possible generally, or almost always information is missing. Any questions about this? I'm going to stop here in today's class. I'm trying to follow the pace that I had last semester. I don't want to go too much faster than that. So we covered Callan's postulate 1 and 2 today. Please get hold of Callan's book and read through the postulates. He also has another postulate, which is really the third law of thermodynamics. We are not going to use that, but go through Callan's book. Next time when we come back, I will try to give you intuition for why these bizarre looking monotonicity relations should exist. I will look at physical examples of trying to put energy into a system and just give you intuition which is not covered in Callan, and then we will proceed from there. So see you on Tuesday.